안녕하십니까 올쇼TV 시청자 여러분, 로데슈바르즈에서 준비한 오늘 웨비나에 참석해 주신 여러분을 환영합니다. 저는 로데슈바르즈의 최지홍이라고 합니다. 오늘 웨비나를 위해서 저희 로데슈바르즈에서 저와 함께 일하는 저희 동료 직원분이 함께 하셨어요. 그래서 오늘 간단하게 Q&A라든지 이런 부분들을 함께 말씀을 드릴 거고요. 오늘 함께 자리해 주신 남찬우 매니저님을 여러분께 소개하겠습니다. 소개해 주시죠.
네, 안녕하세요. 저는 로데슈바르즈코리아에서 기술지원팀에서 근무하고 있는 남찬우라고 합니다.
예, 오늘 저희가 올쇼TV에서는 처음으로 웨비나를 여러분께 선보이는 것 같습니다. 그래서 오늘 준비한 내용들을 가지고 말씀을 드릴 텐데요. 아무래도 저희가 처음 이 자리에서 여러분을 뵙다 보니 여러분들 먼저 저희 회사에 대해서 아시는 분도 계실 수 있겠지만은 간단하게 먼저 소개를 드리고 시작을 하는 편이 좋을 것 같습니다. 그래서 저희 회사에 대해서 간단하게 한번 좀 말씀을 드려야 될 것 같은데요. 남찬우 매니저님, 회사에 대해서 잠깐 말씀을 좀 해주실 수 있을까요?
네. 저희 로데슈바르즈는 독일 뮌헨에 있는 RF 계측 장비를 공급을 하고 있고요. 독일에서 저희가 80년 이상 저희가 RF 계측 장비에 대해서 개발 및 공급을 직접 하고 있고, 그리고 전 세계에도 70개국 이상에 대해서 지사를 두고 저희가 공급을 하고 있습니다. 그리고 한국에도 저희가 로데슈바르즈코리아라는 이름으로 한국 지사를 가지고 있고요. 최근 20년 동안 다양한 이제 RF 관련 어플리케이션에 대해서 솔루션을 공급을 하고 있습니다.
네, 저희가 말씀드린 것처럼 지금 20년 넘게 국내에서 활동을 해왔는데요. 또 오늘 처음으로 이렇게 올쇼TV에서 여러분들을 찾아뵙게 되어서 또 처음 저희 나름대로는 또 준비를 많이 했습니다. 그래서 오늘 웨비나를 위해서 여러분께 말씀드릴 내용들로 준비한 부분들은 최근 특히 자율주행이라든지 스마트 크루즈 컨트롤 같은 내용들을 통해서 우리가 흔히 많이 듣고 있는 차량 레이더에 관련된 내용들로 여러분께 말씀을 드리려고 준비를 했습니다. 오늘 제목에서 보시는 것처럼 좀 더 현실적인 어떤 차량 레이더에 대한 시험을 위해서 어떤 것들을 할 수 있을까, 어떤 솔루션들이 있을 것이냐, 이런 부분들을 말씀을 드릴 수 있도록 준비를 했고요. 오늘 말씀드릴 차량 레이더 시뮬레이션이라고 하는 부분이 어떤 내용들로 이루어지는지 먼저 시작하기 전에 간단하게 한번 말씀을 드리는 게 여러분들께서 이해하시기 훨씬 편하실 것 같아서 간단하게 말씀을 드리고 시작을 하도록 하겠습니다. 남찬우 매니저님, 이 시뮬레이션이라고 하는 부분이 어떤 걸 어떻게 시뮬레이션을 할 수 있는지 좀 간단하게 말씀을 해 주실 수 있을까요?
네. 최근에 이제 아무래도 자율주행에 있어서 레이더 센서가 이제 다양하게 사용이 되다 보니까 그에 대해서도 이제 레이더 센서가 정상적으로 동작을 하는지 검증하는 부분도 점점 필수적으로 자리 잡게 되었어요. 네, 그런 부분에 있어서 실제 도로나 아니면은 진짜 타겟을 가지고 이런 레이더 센서를 검증하는 데는 제약사항들이 있다 보니까 그거를 대신할 수 있는 가상 타겟을 만들어주는 레이더 타겟 시뮬레이터가 현재 지금 많이 사용이 되고 있고요. 현재 레이더 센서도 이제 점점 세대가 거듭함에 따라서 점점점 많은 기능과 또 더 좋은 성능을 가지게 되었는데, 또 그러한 것들에 맞춰서 레이더 타겟 시뮬레이터도 점점 많은 요구사항을 커버하도록 많은 기능들을 제공을 하고 있습니다. 오늘 소개드린 내용에서 그러한 기능들을 한번 참고해 보시면 좋을 것 같습니다.
네, 저도 들은 얘기입니다만은 최근의 차량들은 옛날처럼 자동차라기보다는 이 전자제품에 더 가까워진다, 이런 이야기들을 흔히들 하고 있는 것 같습니다. 이 차량 레이더에 대한 부분도 어떤 면으로 이제 그런 연장선상에 있는 부분이 아닐까라는 생각이 들기도 하고요. 특히 이런 레이더라고 하는 부분은 우리가 생각하는 것처럼 무선 전파, RF라고 보통 부르게 되는데, 이런 부분들이 이제 실제 차량에 접목이 되기 위해서 어떤 식으로 시험을 해서 우리의 안전과 생명을 정말 지킬 수 있을 것이냐, 어떻게 더 편리하게 사용할 수 있을 것이냐, 이런 부분들을 도움을 드릴 수 있는 그런 부분이 아닐까라고 생각이 됩니다. 오늘 준비된 저희 웨비나는 저희 독일 본사에서 글로벌로 진행을 했던 웨비나를 저희가 국내에 맞춰서 자막으로 여러분께 준비를 했습니다. 그래서 여러분들께서 비록 영문으로 진행이 됩니다만 자막을 통해서 내용을 보시는 데에는 크게 문제는 없으실 거라고 생각이 되고요. 또 동영상 웨비나를 진행한 이후에 여러분들께서 올려주시는 질문을 저희가 또 현장에서 또 내용들을 답변을 드릴 예정입니다. 그래서 보시면서 혹시라도 궁금하신 부분들이 있으시다면 언제든 채팅창을 통해서 질문들을 올려주시면 저희가 내용 관련해서 답변을 드리도록 하고요. 또 한 가지 미리 말씀드릴 부분은 여러분들 보셨겠습니다만은 오늘 참석해 주신 분들 중에서 설문 응답해 주시고 질문해 주신 분들을 대상으로 제가 총 30분께 스타벅스 카페 아메리카노 쿠폰을 제공해 드릴 예정입니다. 추첨을 통해서 제공을 해 드릴 예정이니까 여러분들 참석하시면서 궁금하시거나 혹은 코멘트 남겨주실 부분들이 있으시다면 언제든 자유롭게 올려주시면 정말 많은 도움이 될 것 같습니다. 네, 지금부터는 저희 준비한 동영상을 보시면서 레이더 타겟 시뮬레이터라는 게 어떤 일들을 할 수 있는지, 그리고 어떤 부분들을 정말 시험을 하고 결과를 볼 수 있는지, 이런 내용들을 함께 보시도록 하겠습니다. 지금부터 같이 보시겠습니다.
Hello, my name is Andreas von Löseke and I'm a product manager in microwave imaging at Roland Schwarz. So today, together with my colleague Alice Ascher, I'm going to introduce the radar test system to you. So we will start with a quick introduction in the topic, what is new about the test system, what is required, what are the requirements in the field, and then we will go into the test system. First, we will have a look on the front end, and then we will have a look on the back end of the system. We will show you some exemplary configurations, give you some examples, and show you how it could be done. In the end, there's a quick summary, and if there are any questions remaining from your side, you can always contact the product management team or the local sales. So looking at autonomous driving functionality or adaptive cruise control, for example, emergency braking, these are all functionalities which are realized with radar sensors. So here in this picture, you see there's a couple of radar sensors in the car. There's some that are looking farther out. There are some that are looking at targets at a closer range. And all these sensors, they need to cooperate in order to get a working radar environment. So when there's a lot of sensors in the car, there's also a lot of challenges that we are facing. So with the challenges, for example, the problem is that if you want to test all these functionality on the road, you actually do have to have a roadworthy prototype. And there's a lot of other colleagues who want this roadworthy prototype for testing as well, because ADAS not only relies on radar, but also on other sensors like camera, LiDAR, ultrasound. So all these sensors need to be tested, and there's only a limited amount of prototypes to test with. So this is a big challenge to actually get hold of such a vehicle. The problem is also you can't run these tests like 24/7. So you need to schedule them. The day only has 24 days and you can't speed up the real time. So you can't do the testing faster, which you, for example, can do with over-the-air test systems or simulation techniques. Saying over the air, also with most current radar test systems, this over-the-air testing capability is actually missing. So you will see later in the slides that when you test the radar in such an environment, you actually take the radar sensor itself out of the loop and you don't really test the radar sensor. Also, there's limited capabilities when it comes to scenario testing. So there's a couple of like complex scenarios or dangerous scenarios or hardly to reproduce scenarios. So when you have the driver on the road, they are most probably very good drivers, highly reproducible, but it's not as reproducible as running the same test twice in the lab. So what is our solution in this case? The good thing is we can help you speed up your development cycle. So you can speed up not only the testing, but also can you do the parallel testing. So you don't need roadworthy prototypes for all the testing that is required. With our test system, also the over-the-air radar simulation is included. So you're not only testing the ADAS capabilities of the vehicle, but you're also testing the ADAS capabilities of the vehicle with a complete radar environment running. The instrument has a built-in real-time interface, so you can in real-time adapt the scenarios that the system is actually playing. So this is, for example, useful for vehicle-in-the-loop operations. So of course, you do not have to test in a vehicle-in-the-loop configuration. You do not have to test in a hardware-in-the-loop configuration, but this is what the system is supporting, and my colleague will tell you later on more on this functionality. The great thing is also, you can generate very complex scenarios with a high repeatability. And you can also generate these dangerous scenarios, for example, when you're going on the highway at a very high speed and someone is getting into your lane and you probably need to trigger an emergency brake maneuver. This is nothing where you want a test driver to have to sit in the vehicle. Another great thing about a solution is that it's highly scalable. So depending on the application, depending on your requirements, you can actually customize the solution to fit your needs perfectly. So when we look at the Roland Schwarz portfolio, there's a lot of radar testing to be done. And there's a lot of radar testing that we are supporting with our instruments. So when you start with the radar itself is an active sensor, so it's transmitting a signal, and the image you're getting from the environment can never be better than the signal that you're actually transmitting. So in the beginning, you are having a focus on signal analysis. How good is the signal that I am transmitting? How precise is the image of the world that I actually see? And then the most intuitive thing when testing a system that is intended to see targets is actually generating those targets, but pretty defined. So we have this static target generators here, and we have signal generators that you can use for interference testing because your radar isn't the only radar on the road. So you have to simulate all the other radars on the road as well. Then, in the end, there's always the designer who packs the radar behind a design emblem or behind the bumper, such that it's no longer that present on the vehicle anymore, but it's also hidden behind a surface. And you need to ensure that this surface is actually radar transparent. And radars are transmitting signals, so if you want to test the radar just by itself, then we have the shielded chambers as well, where you can perform these tests. So let's have a look in this picture again. So before I said that most other vehicle-in-a-loop test systems, or basically all other vehicle-in-a-loop test systems, are taking the radar out of the loop. So what does that mean? How does that look? So in this case, we see the radar sensor in front of the vehicle, which is used, for example, for adaptive cruise control. But the radar sensor isn't in the loop. So instead of the objects detected from the radar sensor, there are artificial objects injected on the bus. So the radar sensor itself is actually not doing anything, so it doesn't really matter whether the sensor is there or not. It's basically just consuming power, and therefore it's not really tested, and it's not a complete test. So this is a potential source of errors because you don't know how the radar sensor is performing under this specific condition. So with the QAT and the ARIC, you can actually test the radar sensor in the loop directly, in vehicle in the loop. So just to give you an example, how would such a test system look like? In this case, you see there's a couple of QAT 100 front ends. And behind the absorbers, there are standing ARIC 800A as the back end for the target generation or the echo generation. And in this case, we are very strongly cooperating with a company AVL. And we can offer you turnkey solutions for this challenge. So the instruments that we are introducing today do not only work in this vehicle-in-the-loop environment. This is just one example. You can also use them in hardware-in-the-loop environments or just as a benchtop setup. So let us have a closer look on how this system actually works. So when we look at current generation test systems, for example, when we look at this test system, we have the ARIC 800A and we have a standard front end. And in this standard front end, the radar receives the signal. It delivers the signal to the back end. There the signal gets massaged. It gets a Doppler added, a time delay added, and then the signal is getting sent back to the front end and is sent back to the radar. The radar then is analyzing the signal and is detecting the echoes that we have artificially generated. So the challenge with these kind of systems is that we actually have this object just at one position. And if we want to move this one position, we have to move the complete front end. So this requires a lot of hardware and also takes away a bit of the precision, because if you move something mechanically, it will never 100% stand back in the position where it actually was before. So with our test system, with the QAT and the RIC in combination here, the working principle basically is the same. So still the radar sensor is transmitting a signal gets received by the backend, gets Doppler and time delay added and gets transmitted back. But with this system, you can now electronically steer the beam. So you can decide which of the transmit antennas you actually want to use, so to say, where the signal should be coming from. So the RIC and the QAT are, so to say, the missing puzzle pieces for testing autonomous driving functionality. So we have the RIC 800 as the back end, and we have the QAT 100 as the front end. I've already said those systems are highly scalable. So what do I mean by that? Just to give you some quick examples, here's a quite simple, so to say, driving scenario that is still a little bit dangerous, so something you don't really want to test. And you can do this testing in the lab. So therefore, it's just quite simple testing. It's just one object you want to simulate. It's the deer that is actually crossing the road in front of you, and you want to trigger this emergency braking. So in reality, it's a quite challenging task. For the test system, it's a quite basic task. So in this case, like autonomous or adaptive cruise control, for example, very simple task here where we just want to simulate one object that, for example, we want to trigger this braking functionality, or that should be followed. Quite simple scenario, one backend, one frontend as a combination is enough. We only need one target. Let's have a look at this more complex driving scenario. So where we have the a tunnel scenario, for example, or a city scenario where we have several vehicles on the road, different lanes, and we want to follow one of those vehicles, and we need to detect with the cross traffic alert that we're not changing lanes while the lane is still occupied by another vehicle. So those are more targets. So with this test system, you can have more than just one target. And depending on the amount of backends, so Alois Ascher will tell you more information about that, you can scale the number of targets that you simulate. And with the front ends, you can also scale the angular coverage that you want to deal with. So you can also stimulate multiple radar sensors at the same time. I mean, as long as those sensors aren't interfering with each other, which they shouldn't because they are in the same vehicle. So there's a very high scalability with this system. So what does that actually look like? So scalability, I already touched what I mean by that. And also, when I said you can do multiple radars at a time, in theory, you can also do like a 360-degree radar simulation. So you can simulate, like on the highway, a target that is coming from behind is passing the vehicle, and then you are following this target again. So 360-degree coverage. And the system by itself acts as one instrument. So you don't have to take care that the front end actually is somewhere else. And the back end, you need to communicate with the back end and the front end separately. No, that's not the case. You only need to communicate with the back end, and the back end takes care of all the communication with the front end. So to simplify it even more, the back end has an open simulation interface. So basically it takes all the commands and then translates it to the QAT, which then does the angular simulation. So of course we also have worldwide support. So no matter where you are sitting, there's always a Rot und Schwarz application engineer or a sales engineer, which is happy to assist and happy to help you. Let's have a look at the front end. So as I said, system is consisting of the front end and the back end. And both instruments do have some unique functionalities which perfectly plays together with the respective instruments. So looking at the front end, what we see and what we see also here is we have a huge amount of transmit antennas. So we have 96 transmit antennas, and you probably don't see them due to the missing resolution, but there's one transmit antenna about every 4 millimeters. So we have a very high resolution. And we have, depending on the distance where you put the QAT, you can decide what is the resolution that I want to cover and what is the angle that I want to simulate targets at. Also, the front end supports 4 gigahertz bandwidth, so all current state-of-the-art radar sensors are supported. And also, the solution is very scalable. So, as I said, you want to cover more of those. You simply remove the handles and stack the instruments next to each other, and then you have this smooth 360 or up to 360 degree coverage. So the surface here, this is absorber. So when you have a standard system with these gain horn antennas, the antennas itself have a quite high radar cross-section, so they are visible in the radar. With the QAT, you don't see these targets because the surface is covered in absorber, so you don't really see any reflections coming from there. So 4 millimeter antenna spacing, this makes it pretty accurate and pretty precise. And also you can rotate this instrument by 90 degrees if required, because all the antennas are 45 degree polarized. And in this case, you can then do elevation simulation. So if very short distances are required, the cool thing is, usually you have the cabling between the front end and the back end. So with this system, you have the capability to actually put an analog step delay line directly into the front end and then simulate very close range targets. So in this case, so to say the back end and the front end is somewhat in the same instrument, so there's absolutely no cabling. And the longer distance targets can then be produced by the RX 800A. There's no mechanical movement required. So if you want to simulate a target from here, for example, there's no need to actually move anything. You simply switch on the antenna at this position, and then the target can move this direction, can move back and forth. You can have 2 targets crossing each other. So all this is possible without any movement. And this makes the system actually quite immune to vibration. So if you're thinking again of this vehicle in the loop test stance, where you have the vehicle and everything is shaking and vibrating. So with the standard mechanical setups, it's quite challenging to set up something reliable here. The QAT and the RX simplifies this setup a lot. So let's also have a quick look on the back of the instrument. So you see there's a lot of SMA connectors, and that is because the QAT itself is divided into segments. So on the instrument, you see this line of transmit antennas, and we can separate this line of transmit antennas into 4 segments, and you can connect an individual IF to each of these segments. So Alois Ascher will also touch this topic later, so you will understand what I mean by that and why this adds even more flexibility. It's tough to see because you don't know how tall I am, so it's tough to relate how huge these or how large these instruments actually are. So you see it's roughly 40 centimeters, and depending on the angle that you want to cover, you stick them together. So when you are in a lab environment or when you are in a vehicle in a loop chamber, one of the big challenges you are facing is there's a lot of reflections coming from everywhere. And there's a lot of distortions, and you also don't want to distort the other testing that is done nearby. So what do we have for that? For this, we do have the QAT 100Z50. So that basically is a shielding kit that mounts on front of the instrument. You can put the QAT on one end of the shielding, and you can put the radar under test on the other end. And thus you have, so to say, an undisturbed environment, reflection-free, and it's more or less noise-free for testing, and you also do not disturb the neighboring setups. So I mentioned before, depending on the angular coverage that you require and also the angular resolution, you can either bring the instrument closer to the device under test or you can get it farther away. So it's just some mathematical formulas. And basically, to simplify the task, I've created this table just to give you an overview. So you see that with 500 millimeters of distance, that is basically what the QATZ50 is giving you. You're covering a field of view of roughly 40 degrees, so plus minus 20 degrees, at a resolution of 0.4 degrees. So if you say 0.4 degrees, that's not the resolution I want, then why not put the QAT farther away until you reach the resolution you want? And then you do probably have to put a little more instruments in there and actually cover the angles that you want to cover. So how does it look like when we put these instruments next to each other? So what you see here is we have an example of 3 QATs next to each other. So I remove the handles. And then in this case, you just have 54 millimeters between the antennas. So that's why we always propose to use an uneven number of QATs, because in this case, if you use a even number of QATs, you would have this gap exactly in the middle, and that's where you usually require the highest resolution. So why not shift this gap to the left or to the right, have the very high resolution in the middle, and where the radar doesn't have the high resolution anyway, we have this small gap. So what does the signal processing in the QAT look like? So on the right-hand side, you see the radar sensor. The radar sensor in this case is transmitting at 4 gigahertz, and we are receiving with either 1 or 2 receive lines of the antennas. So after that, there's a 4 times multiplier. So behind that 4 times multiplier, we just have 1 gigahertz bandwidth. So what is called the narrowband backend with 1 gigahertz is actually sufficient to fully play with a 4 gigahertz radar. So in this case, we have this signal conditioning unit, which has the capability to put out either the whole antenna line on just one SMA connector, or put out all the 4 segments individually. You can also optionally connect one of these analog step delay lines to simulate the very short distances. Optionally, you can have a second line, and also for this second line, you have the ability to have an analog stepped delay line again. Then you have the connectors to the ARIC. The ARIC does the main part of the signal processing, transmits the signal back. We are multiplying the signal times 4 again, so we are again at 4 gigahertz bandwidth, and the radar sensor receives the signal and actually has to work with what you get and will detect all the echoes. So much on the front end. So now let me hand over to my colleague who will give you all the details on the back end.
Yeah, thank you, Andreas, for the nice introductory words and also for the presentation of the QAT Advanced Antenna Array. I am Alois Ascher, I'm Product Manager for Signal Generators, and I will show you now the Radar Test System backend, so the ARIC 800A, and I will also give you a short introduction in some exemplary configuration and the related applications. So, but before we start with the ARIC 800A in technical details, I just want to give you an idea why it was so important to have an advanced radar echo generation instrument together with the QAT 100. And that's because advanced tests during R&D of automotive radar sensors or of even advanced driver assistance systems or autonomous driving require dynamic variation of artificial objects. And what are the parameters that have to be dynamically adjusted? Those are typical the distance of the artificial objects, the size, so the radar cross-section, the radial velocity, so how the object is moving with respect to an ego vehicle, for example, and the angular direction. And if we think a step further, then higher levels of autonomous driving and more advanced ADAS features typically require multiple radar sensors that are taken into account via sensor fusion for certain functionalities. And all of those radar sensors which are participating in such advanced functions have to be stimulated in a synchronized and simultaneous manner. And with the R&S REC 800A, we can cover those requirements. So what is the REC 800A? The REC 800A, first of all, is a dynamic radar echo generator. It can generate dynamic objects down to very short distances. We can simulate multiple independent objects. I'll show you later what multiple means for different configurations. And of course, we also support very high instantaneous bandwidths to also be able to generate artificial objects even for the most modern short-range radar sensors. So the REC 800A, when operated together with the QAT100, which Andreas explained before, only requires 1 gigahertz of IF bandwidth, is supported by the REC 800A. But beside that, we also have the possibility to extend the IF bandwidth all up to 4 gigahertz. And with this IF bandwidth and classical millimeter wave remote front ends that I will show you later, you also have the possibility to use more of a classical approach for radar testing, for example, for early benchtop test cases or for test cases which require the usage in a compact antenna test range chamber, for example. Scalability is an important topic when talking about the REC 800A. So we are very proud that we have with the REC 800 and the QAT100 a really scalable solution, which are also fully harmonized with each other. So they are not working like two separate instruments. They are working together like one system, like one instrument. And of course, we also want to make sure that the REC 800A or the radar test system is working seamlessly inside of environmental simulation environments. And therefore, we also have a built-in real-time interface, which is very fast and very responsive. So what are the front ends that we support with the REC 800A as backend? The first front end is obviously the QAT100, which Andreas explained already to you. The second possibility of front ends that we have are more or less the classical millimeter wave remote heads that you perhaps know from the REC 100A, for example. So there are several possibilities available for 24 gigahertz, for 76 to 77 gigahertz, and also for 76 to 81 gigahertz. And with this, high amount of different configurations options, we have a perfectly tailored setup test solution that exactly fits your testing needs. And what are possible test cases or use cases for our instruments? First of all, of course, production. Then the second use case is during the R&D process of a new radar sensor, so benchtop testing. And then if the radar sensor is more or less functioning, then we go, or there is typically the step towards hardware in the loop tests to verify the sensor under certain ADAS relevant circumstances. And then we have the last step, which is vehicle in the loop testing. So you have your full vehicle, you place the vehicle on a dyno, and then you perform all kind of ADAS relevant tests with the vehicle on the roller dyno. And for all of these applications, we have a fitting or tailored test solution. So for production use case, we have our REC 100A and also the REC 800A, which can be configured in a suitable way. So the REC 100A more for the simpler production use cases, and the ARIC 800A if more advanced tests should be performed during radar sensor production. For benchtop R&D, you can basically use the whole portfolio. So the ARIC 800A together with all the front ends that we have available. So the QAT 100 or the millimeter wave remote heads. And last but not least, for hardware in the loop and vehicle in the loop, the key is to use the ARIC 800A together with the QAT 100 because they are tailored or they are designed especially for that functionality test cases. So now let's have a look on the ARIC 800A. So first of all, to give you an idea, I also have it here on the table. So we have here a 5 height unit instrument, which exactly also fits the 19-inch width so that it can easily be integrated into test racks. And if we turn the instrument around, then you can see we have here some sort of modules that I highlighted here in red. And those modules have specific use cases. So the module itself, or a single module itself, basically is an individual target or echo generator. Generally, the ARIC 800A follows a hybrid echo generation concept. What does this mean? So a module, which can be 4 as a maximum, 4 installed into a single base unit, consists mandatory of a digital baseband and of an IF switching board. So the digital baseband is basically the digital target simulator itself, and the IF switching board is the last step before the signal is routed inside of the digital baseband or routed outside of the digital baseband. And that IF switching board typically is used to adjust the signal power levels and smoothen the amplitude flatness of the return signal to the radar sensor on the test, for example. If the digital baseband is not covering all testing needs from your side, so for example, the digital baseband has a minimum distance of lower than 17 meter. If you want to generate scenarios that have artificial objects that are closer than that 17 meters, you can optionally install next to the digital baseband an analog step delay line. And this optional analog step delay line then allows you to simulate, for example, autonomous emergency braking scenarios, which require object distances closer than 4 meters, for example. And what does this mean if we sum it up? We have up to 4 modules that can be installed into a single ARIC 800A base unit. Each module consists of a digital board, which is the digital echo generator, IF switching board, which is used to adjust the signals and power level wise and amplitude flatness wise. And last but not least, we have the analog step delay line, which can also be installed optionally into a module for the short object distance coverage. So much about the internals. Now let's have a closer look into certain setups. And as I mentioned before, scalability was a major part in our when developing our instruments. So I will show you some highly scalable use cases here, which are exactly following this philosophy. And for this, I want to start here with the setup on the left side, which is an ARIC 800A, which is fully connected with all possible IF paths to the segments of a QAT 100 antenna array. So to a single QAT 100 antenna array. So let's start with an empty box, so to say. So we have here the QAT 100 on the left, and we have the AREC 800 here on the right. If we have the simplest configuration, then it would mean, okay, we have one digital baseband that is installed into the AREC 800A base unit. And with this digital baseband, you have one individual object that can be generated by this digital baseband and routed to the QAT100 antenna array. Now, as I mentioned before, perhaps you want to perform autonomous emergency braking tests. Then you would include an analog step delay line in the same module, which is then interconnected to the digital board. So the digital domain and the analog step delay line thereby perform a seamless handover. So for the radar sensor under test, it's not visible whether the object is generated in the analog step delay line or in the digital board. Now let's say, okay, I now have one IF path connected to my QAT, but I want to have more than just one object available. Then you can, inside of a module, activate a second IF path via a key code. So in this case, you just install the key code on the AREC 800A and a second digital output is activated, which then can be routed to the QAT100, which means then you have two objects that can be generated. And if we scale everything up and we make the AREC 800A fully loaded, then you can have up to 8 digital paths and up to 4 analog step delay lines, which means you have up to 8 individual objects that can be routed to an QAT100 antenna array. And out of the 8 objects, up to 4 objects can be generated via the analog step delay line for autonomous emergency braking tests, for example. So much about the first setup. Now, let's think of another use case. Perhaps you do not want to simulate a very dense scenario, but what you want to do is you want to test a corner radar sensor which covers a very wide field of view. And in this case, multiple QAT100s are connected to a single AREC 800A base unit. How does it look like in this case? So from the overall configuration of the AREC 800A, it's basically the same as before. So you have up to 8 digital outputs, and you have up to 4 analog step delay lines installed of the AREC 800A base unit. The only difference now is that instead of routing all of the signals that are coming out of the AREC 800A to a single QAT100, we now route each of the IF paths to an individual QAT100. That means you can connect and control up to 8 QAT100s with a single AREC 800A base unit, which is great because then you can cover a really wide field of view and can test corner radar sensors in a very easy and convenient way. And I already mentioned the alternative front ends, the millimeter wave remote heads for benchtop test cases before, and those, or for operation with those, the configuration of the AREC 800A also looks a little bit different. So let's have a closer look. In this case, we have here again our AREC 800A base unit. Then we install the first digital board inside of the AREC 800A, which allows us to connect the AREC 800A with one of those millimeter wave remote front ends with up to 1 object per default from each digital board. But in this case, if the millimeter wave remote front ends are used, you can install key codes in the AREC 800A base unit, which allows you to generate up to 8 individual objects now per IF path. So that means we have here one remote head connected, and up to 8 objects can be now generated from that one remote head. But obviously, we do not have the advantage here of the QAT that those objects are generated from different directions, from angular directions. All appear like from the same angular direction, from the same incident angle, but are dynamic in terms of distance, velocity, and radar cross-section. Of course, we also have the possibility here to install an analog step delay line inside of the base unit, which then allows you to generate objects that are in the close range. And if we scale everything up and we fully load the RX 800A, you have here the possibility to connect up to 4 classical millimeter wave front ends to a single base unit. You can generate up to 8 objects from each of those front ends, so 32 in total. And you also have here the very high bandwidth support, so you can also test here automotive radar sensors with instantaneous bandwidth of 4 gigahertz. If we sum everything up, what I've shown you now in terms of scalability and flexibility, we can see, okay, on the left side, we have our RX 800A together with the QAT 100. In this case, we can generate up to 8 individual objects coming from up to 8 independent angular directions. So that means RX and QAT can generate up to 8 objects maximum when used in combination or used together. In contrast, on the right side, if you use the classical millimeter wave remote front ends, you can connect up to 4 to a single base unit, and from each of the 4 front ends, up to 8 individual objects can be generated. That means up to 32 objects in maximum configuration here. But with the limitation that you cannot generate the objects from different or with varying angular directions without mechanical movement. Another important part when talking about scalability and flexibility is the synchronization of front ends. And how is this performed? So the RX 800A is the core element in this case of the test system. All front ends that are used, in this case, for example, for wide field of view coverage, are connected to the RX 800A. And the RX 800A controls and synchronizes all of the front ends that are used within the test setup. And additionally, the RX 800A also interfaces to third-party simulation environments via a dedicated hardware-in-the-loop interface. If we scale the setup that I've shown you a little more up, then one possibility would be to use an individually RX 800A per front end used in the test system. For example, if you want to simulate very dense scenarios with a lot of artificial objects. Then all RX that are participating in the test setup can be configured in a primary, secondary configuration. So you have one primary instrument, and then this primary instrument interfaces to the simulation environment and syncs and controls all secondary RX 800As that are used in the test system. And last but not least, I also teased that before, we have the possibility with the classical millimeter wave front end to validate 4D automotive radar sensors, which have typically very large apertures, large antenna arrays, together with the ATS 1500C, the compact antenna test range, shielded chamber, and therefore have the possibility to test those automotive radar sensors with very large antenna arrays under far field conditions in a very compact format. Now let's go to the exemplary configurations. And therefore I prepared 3 examples which are mainly based on the configurations of the RX 800A, which I have already shown you. So what is the first configuration? That is the, I would say, typical radar sensor validation if the RX 800A is used together with the ATS 1500C shielded chamber. What does a setup that can address the test cases consist of? It consists of one RX 800A echo generator. It consists of an RX millimeter wave remote front end. And last but not least, it consists of an ATS 1500C shielded chamber. And what are the key features that can be tested and can be addressed with such a setup? Of course, we support the 4 gigahertz of instantaneous RF bandwidth. We are fully harmonized with the ATS 1500C and the COD-R reflector. We can generate up to 8 dynamic artificial objects because inside of the chamber only one remote head can be installed. And those dynamic artificial objects are individually controllable in terms of artificial object distance, in terms of object size, and also in terms of radial velocity. Of course, we also have IF input and output interfaces in such a configuration, which allows you to connect external instruments such as signal and spectrum analyzers or signal generators for addressing even more T&M tasks in such a system. And last but not least, of course, we also have the possibility to connect the real-time hardware or to use the real-time hardware in the loop interface. So what is the second configuration that we can think of? This one would be more usable for basic ADAS feature tests. And what does a setup for basic ADAS feature tests consist of? One RX 800A as backend and one QAT100 advanced antenna array as front end. What are the key features of such an exemplary basic ADAS function test? So we have 4 gigahertz bandwidth with the QAT100 together. And for basic feature tests, we think 2 dynamic artificial objects are sufficient in the setup. And those dynamic artificial objects can be controlled in distance, object size, radial velocity, and in this case also angular direction or azimuth. And which is not shown here, of course, we also have the hardware in the loop interface, because for that ADAS feature tests, typically simulation environments are required, and those simulation environments can be connected via the hardware in the loop interface to the RX 800A. So, and the last example, the last exemplary configuration I want to show you is a setup for advanced ADAS feature tests. We have, again, a very similar setup. We have one RX 800A, but in this case, 3 QAT100 advanced antenna arrays as front end. We again have the possibility to cover 4 gigahertz of instantaneous bandwidth, but in this case, for advanced ADAS feature testing, we think 6 dynamic artificial objects are the minimum. And each of the object is again, controllable in distance, RCS radial velocity, and angular direction. We again have the support for the hardware in the loop interface to interface with third-party simulation environments. And last but not least, what's very important in this case for the advanced ADAS feature test is that we have, thanks to the 3 QATs in the setup, the capability to stimulate multiple radar sensors in parallel. And this allows driving scenarios as exemplary shown on the right. For example, a cutting-in scenario on a highway. So a car is overtaking and is cutting in front of the ego vehicle. And the first radar sensor that is stimulated is the side-looking radar, which detects the object, and then it slowly leaves the field of view of the side-looking radar and enters the field of view of the long-range radar. And so, very complex or very advanced features can be tested with such a setup. So this brings me to the last point, so the summary, and I want to keep it short. So generally you can see here we have a whole lot of unique points when talking about the ARIC 800A and the QAT 100. I just want to highlight the most important ones. So we can generate dynamic artificial objects in very short distances. We can have multiple independent objects be generated without any mechanical movement. And what's also very important is that we have an HIL interface, a hardware-in-the-loop interface, that allows the connection to all the established simulation environments. And last but not least, we always say, hey, we have a very scalable and flexible solution with the ARIC 800 and the QAT 100. And that is more or less the core point I want to highlight in the end. Last but not least, I want to say orders for the system can be placed, and feel free to get in touch with our sales force to get further information regarding the ARIC 800A and the QAT 100. And thank you for your attention.
네, 지금까지 저희가 준비한 그 동영상 웨비나를 내용을 함께 보셨습니다. 그래서 오늘 그 레이더 시뮬레이터가 무엇인지, 그리고 어떤 일들을 할 수 있는지, 어떤 그 기술적인 내용들을 우리가 담당할 수 있는지, 이런 부분들을 저희가 쭉 말씀을 드렸던 것 같아요. 남찬우 매니저님, 오늘 진행됐던 내용들을 뭐 간단하게 시간 관계상 아주 짧게 한번 요약을 좀 부탁드리겠습니다.
네. 이제 레이더 타겟 시뮬레이터라는 것이 결과적으로 이제 레이더 센서가 정상적으로 동작하기 위한 시나리오를 만드는 테스트 장비라고 보시면 되거든요. 근데 이제 최근에 이제 레이더 센서의 요구사항 중에 하나가 바로 이 좌우 각도에 대한 부분이었는데요. 네, 이런 부분을 기존의 레이더 타겟 시뮬레이터는 이제 프론트엔드 방식을 이제 왼쪽이나 오른쪽으로 이렇게 움직이는, 물리적으로 움직이는 방식으로 구현을 했었어요. 네, 그런 부분이 QAT라는 이제 새로운 솔루션을 통해서 이제 전기적으로 이제 안테나를 스위칭하는 방식을 사용하게 되거든요. 네, 그런 부분이 있으면은 프론트엔드를 이제 물리적으로 움직이지 않고 이제 좌우 각도를 이제 정밀하고 정확하게 모살할 수 있다. 그런 솔루션을 저희가 출시했다라고 보시면 좋을 것 같습니다.
그러면 실제 레이더가 동작하는 환경에서 다른 차량과의 관계라든지, 아까 잠깐 보니까 추월하는 환경이나 이런 이야기도 좀 나왔던 것 같아요. 이런 부분들까지 우리가 이제 전자적으로 시뮬레이션이 가능하다, 뭐 이런 부분들이 이제 가장 우리가 실제적으로 얻을 수 있는 장점이 된다, 이런 말씀이신 것 같습니다.
네, 맞습니다. 그래서 레이더 이제 주변에 어찌 보면 이제 차량이 주행 중에서 이제 점점 많은 차량을 마주할 수가 있거든요. 네, 그런 부분에 있어서 이제 뒤에 있는 레이더 타겟 시뮬레이터가 어떻게 지금 타겟에 대한 각도, 아니면 크기, 거리, 이런 것들을 이제 모사해서 이제 실제 레이더 센서가 이제 정해진 알고리즘에 따라서 뭐 제대로 속도를 멈추는지, 아니면 속도를 더 내는지, 아니면 차선을 바꾸는지, 그러한 기능 테스트가 가능하다고 보시면 될 것 같습니다.
네, 오늘 진행된 내용 저희가 그 차량용 레이더에 대한 내용으로 말씀을 드렸는데요. 오늘 정말 많은 관심을 보여주신 것 같아요. 질문도 정말 많이 올라왔는데, 오늘 저희 진행 시간 관계상 저희가 이 내용들을 다 여기서 답변 드릴 수는 없을 것 같습니다. 그래서 오늘 일부 그 질문에 대해서만 우선 답변을 먼저 여기서 드리고요. 나머지 부분들은 또 저희가 추후에 그 각 질문하신 분들께 다 따로따로 회신을 드려야 될 것 같습니다. 그래서 우선 그 질문하신 내용 중에서 김병수님 올려주신 질문이 있어요. 이 부분 그 저희 제품에 대한 부분이랑 뭐 기타 내용들로 해서 한 4가지 질문을 한꺼번에 올려주셨는데, 요거 답변 한번 부탁드릴 수 있을까요?
네. 김병수님께서 많은 질문을 주셨는데요. 첫 번째로 RX 800A의 이제 입력 신호에 따른 에코 신호를 발생시키는 기기인가요? 라고 말씀해 주셨는데, 말씀해 주신 대로 레이더 타겟 시뮬레이터라는 이제 시스템 자체가 레이더 센서가 쏜 FNCW 신호를 이제 받아서 그거를 이제 사용자가 원하는 파라미터에 의해서 이제 수정을 하게 되거든요. 근데 그런 신호를 이제 저희가 에코 신호라고 표현을 하게 되는데, 이런 에코 신호를 레이더 센서에 다시 되돌려줘서 이제 가상 타겟을 탐지하게끔 만드는 장비라고 보시면 좋을 것 같고요. 그 두 번째로는 QAT100은 RX800A에 신호를 보내주는 안테나 역할을 하나요? 라는 질문에 대해서도 이제 말씀해 주신 대로 QAT100은 이제 96개의 TX 안테나를 가지고 있어요. 그래서 실제 좌우 각도에 따라서 이제 사용자가 설정한 안테나를 이렇게 스위칭을 하거든요. 그래서 이제 프론트엔드를 움직이지 않고 좌우 각도를 모사할 수 있는 그런 안테나 역할을 한다고 보시면 될 것 같고요. 그리고 AVL에 대해서도 언급을 해주셨는데요. AVL은 이제 Vehicle in the Loop 솔루션을 공급하는 업체거든요. 근데 저희가 실제 이런 Vehicle in the Loop라는 이제 테스트를 할 때 레이더, GPS, LTE, 여러 가지 주변 신호들을 이렇게 모사하는 환경을 구축을 해야 돼요. 근데 그러한 부분에 있어서 레이더 환경을 구성하는 것이 바로 이 RX800A의 이제 역할이다라고 보시면 될 것 같습니다. 그리고 마지막으로는 이제 R&S의 RX800A와 QAT100을 사용하는 주요 기업에 대해서 알고 싶습니다라고 해주셨는데 이런 부분은 저희가 좀 공개적으로 말씀드리기는 어려워서 저희가 주요 사용 사례 같은 것들은 따로 저희가 메일로 전달드리도록 하겠습니다.
예, 시간이 지금 살짝 넘어가고 있는데요. 여러분들 화면에서는 아마 안 보이실 것 같은데 지금 저희가 보고 있는 이 앞에 모니터에는 아주 빨갛고 크게 타임오버라고 지금 적혀 있습니다. 그래서 저희가 굉장히 지금 땀이 나고 있는 상황인데요. 그렇다고 해서 저희가 전부 다 이메일로 처리해드리기 조금 어려울 것 같아서 그 질문 중에서 하나 정도만 더 말씀을 드리고 끝내볼까 싶습니다. 그래서 문태진님 질문해 주신 내용이 있는데요. 요거 어떻게 간단하게 좀 정리 한번 해볼 수 있을까요?
네. 질문해 주신 부분이 이제 레이더에 대한 기반 기술이 이제 특정 업체에서 이제 하는 걸로 알고 있다. 그리고 로데슈바르즈에서 이런 원천 기술을 소유하면서 레이더 제품을 생산하느냐에 대해서 질문을 주셨는데요. 저희 로데슈바르즈는 레이더 센서 자체를 이제 생산하고 있지는 않아요. 근데 대신에 이런 FMCW 또는 이제 PMCW를 사용하는 레이더 센서 제품들이 있거든요. 이런 제품들을 실제적으로 정상적으로 동작하는지 검증하기 위해서 저희가 그런 테스트 솔루션을 공급을 하고 있다라고 생각하시면 좋을 것 같고요. 실제 현재 지금 차량에서 사용하고 있는 레이더 기술 자체가 FMCW라는 기술을 사용하고 있는데 그런 기술은 실제 특정 업체에서 이렇게 독점적으로 공급하고 있는 기술은 아니라 약간 업계 전반적으로 사용하고 있는데 각자의 어찌 보면 노하우를 가지고 장단점을 가진 솔루션을 공급하고 있다라고 생각하시면 좋을 것 같아요.
예, 오늘 저희가 시간 관계상 더 많은 질문들에 대해서 말씀을 드리고 싶습니다만은 좀 어려울 것 같습니다. 어쨌든 오늘 정말 많은 관심을 보여주셨는데요. 오늘 말씀드린 솔루션들을 포함을 해서 저희들이 또 그 4월 13일부터 열리는 전시회에도 저희가 참석을 합니다. 코엑스에서 열리는 전시회인데요. 여러분들 만약에 그 현장 방문하실 수 있다면은 또 저희들과 현장에서 또 저희가 가지고 있는 유니크한 솔루션들을 직접 보여드리면서 또 말씀드릴 수 있는 좋은 기회가 될 것 같습니다. 다시 한번 말씀드립니다만은 오늘 저희 질문 올려주신 분들 정말 많은 분들께서 많은 관심을 보여주셨는데요. 이런 부분들 저희가 현장에서 지금 라이브로 바로 말씀 못 드리는 분 정말 죄송하고요. 이분들께는 저희가 따로 저희가 이메일을 통해서 다시 회신을 드리고 말씀을 드릴 수 있도록 저희가 따로 준비를 하겠습니다. 제가 알고 있기로는 지금 화면에 여러분들 저희 연락처가 또 나갈 거예요. 그래서 여러분들 혹시라도 더 궁금하신 부분이 있으시거나 추가로 필요하신 부분들이 있으시다면 언제든 편하게 저희 쪽으로 연락 주시면 저희가 그에 맞춰서 내용 또 회신 드리고 또 저희 쪽에서 준비한 내용들도 또 말씀드릴 수 있도록 그렇게 할 준비를 하겠습니다. 오늘 올쇼TV에서 처음으로 저희 진행한 이 웨비나 여러분들 정말 다시 한번 많은 관심 보여주셔서 감사드립니다. 오늘 저희 준비한 내용 여기서 정리하도록 하고요. 또 다음번에 또 다양한 내용, 또 흥미로운 내용들로 또 웨비나 준비해서 찾아뵙도록 하겠습니다. 오늘 참석해주신 모든 분들께 다시 한번 감사드립니다. 안녕히 계십시오.